Good morning, everyone. Let's get started this morning. So we had our test Wednesday night. I hope it went well for everybody. I hope we'll have scores posted into next week. So hopefully Monday or Tuesday we'll get scores up. We'll talk about what the scores look like overall. So let's put that behind us. Let's move forward into chapter 4. So our next midterm will be the next 3 chapters, so chapters 4, 5, and 6. I don't need to talk too much about the need to come to class because you guys are here, so I'm glad to have your guys' attention here in person. And if you're watching this relatively soon after today's lecture, good job. I think the tendency after a test is to be like, oh, okay, we can take a week off. And there's not a lot of time in a class like this to take a week off. So glad you guys are here. And like I said, if you're eventually watching this over the weekend, good job. If you're watching this 3 or 4 weeks from now, I don't know, be careful. Chapters 4, 5, and 6 are almost uniquely different from each other in their topics. Like chapter 4, you'll see here is on aqueous reactions, aqueous properties. Even chapter 4 itself has almost different flavors. The first half is on trying to understand how different compounds behave in water. And then the second half gets into like oxidation numbers, so we can predict when substances are changing electrons through a reaction. The next section after that is on molarity, if you remember calculating moles per liter. And then the last section's on like titrations and reaction problems and stoichiometry, and gets very complicated as well. And then we get into chapter 5, which is on thermodynamics, delta H's of reaction, if you remember those. Some aspects of chapter 5 I think are really easy. Some aspects are kind of complicated. So chapter 5 is a different flavor from chapter 4, has a lot of ideas in it, some of which will make sense, some of which will be a little bit, take some energy to understand. And then chapter 6 is on electronic structure of matter, so it gets into the behavior of electrons. So 3 very different chapters that are going to be on our next test. So we'll have our work cut out for us for the next month. Okay, and so chapter 4, like I said, was on aqueous reactions or aqueous properties. So we'll start section 1 with some discussion of what an aqueous solution is, some different terminology, how we can understand what's going on at a molecular level. We'll look at precipitation reactions. You guys have done one of these already. A precipitation reaction is one generally where you're starting with 2 solutions, so nothing solid present, and you mix them together and you form a solid during the reaction. So one example of a precipitation reaction would be something like lead nitrate plus potassium iodide forming lead iodide solid, and then plus KNO3. If we want to put this into balance, we'll do a 2 and a 2. And the key here is that you're making this solid where we started everything else that's dissolved in water and isn't a solid. So we're taking 2 solutions, mixing them, getting a solid that forms. And so that's the basic idea of what a precipitation reaction is. And so we'd like to be able to predict when those types of reactions will occur depending on what types of solutions we're mixing together. So we'll look at that here in chapter 4. We'll talk about acids and bases and their acid-base reactions, the neutralization reaction. And then we talk about oxidation, reduction reactions. So we pick up 3 categories of reactions that we can kind of add to the category of combination, decomposition, combustion. We're going to pick up precipitation, acid-base reaction, and then the oxidation, reduction reaction in this chapter. And then we'll talk about concentrations of solutions at molarity unit. So you might remember molarity is mole over volume. And then we'll work out some stoichiometry problems towards the end of the chapter, where we'll see this mole over liter unit can allow us to solve problems just like we did in chapter 3 with molar masses and masses of reactants and products. Here we'll deal with moles per liter, concentration units of our reactants and products, and relate them to the reacting units in our reaction of moles or molecules. Okay, so let's take a look at what goes on in a solution. So solutions, when we say something's a solution, usually we're referring to a homogeneous solution, so a perfectly mixed solution. There has to be 2 or more pure substances present in the solution. Otherwise, it would just be a pure substance, of course. We have to have at least 2 different things. And then the solvent is whatever's present in the greatest abundance, usually obviously going to be a liquid. And then all the other substances are referred to as solutes. And so the solutes are the things dissolved in the solvent. And then most often, especially for this chapter, because this is the aqueous solution chapter, this is dealing with cases where the solvent is water. So when water is the solvent, the solution is termed an aqueous solution. And then you can refer to the dissolved particle, the solute in these solutions, with that little AQ tag. And so if you have methanol mixed with water, you might refer to methanol as methanol AQ, referring to the aqueous solution of methanol in water. You can also have something like sodium chloride dissolved in water. We can refer to that as sodium chloride AQ. Obviously, NaCl AQ is different than NaCl solid. NaCl solid would just be, a salt crystal, and then NaCl AQ is where that salt crystal's been dissolved into water. So the AQ, of course, just means dissolved in water. Now we're going to see that the behavior of something like methanol is actually drastically different from the behavior of something like sodium chloride in water. And the way they dissolve is a bit of a different sort of process and understanding of why it is that they're mixing together. To be fair, we don't talk a lot about solutions and why they mix together until chapter 13 in Chem 1220. So we come back to solutions. So solutions is actually the title of chapter 13, so you can understand. There'll be more math, more understanding of solutions then. But methanol is mixing also due to a consequence that we talked about in chapter 11 on liquids due to the way it interacts with water. So something like methanol mixes with water due to having a very similar intermolecular force of attraction that the water molecules have for each other. Now, something like if you took butane or pentane or octane, they're not going to mix with water very well because they don't have that mutual intermolecular force. Now, mutual intermolecular forces isn't something I expect you to predict. Looking at two molecules and say, should they mutually interact with each other, that's something we'll see in chapter 11 in more detail and also in chapter 13 and 1220. Here in this chapter, we're going to get into the properties of how something like methanol, which is just the methanol molecule mixing with water, so just kind of forming that homogeneous solution where the two molecules are just interdispersed. If we contrast that with sodium chloride, a much different process. So when we picture a salt crystal where you have millions of ions interacting with each other, that if something like sodium chloride or any ionic compound is going to dissolve in water, if the compound dissolves, it has to do so because water is going and making like little clusters with each of the ions individually. So if you imagine dissolving like a mole of sodium chloride in water, then you're going to have each one of those ions, one at a time, become surrounded by its own little sphere of water molecules. So you're going to end up with an Avogadro's number, 6.00 times 10 to the, or 6.022 times 10 to the 23 sodium cations, the same number of chloride anions, completely surrounded by water. So you make these little spheres of the cations and the anions. And so let me zoom in here. So the purple here are the sodiums, and then the greens are the chloride. And so then when we have a solution of sodium chloride, we have a solution of dissolved ions. With the sodium chloride, we don't have ions present with the case of methanol. Most of our molecular compounds aren't going to interact with water in such a way that they dissociate, or that they're not going to dissociate very much if they do dissociate a tiny little bit. You might have learned that water dissociates a very, very small portion into H plus and OH minus. And this is where water gets its pH from. So the pH of 7 of neutral water means that you have 10 to the minus 7 moles of hydroxide ion in the solution. Very, very small percentage of water molecules. Less than 10 to the minus 5% of water molecules are dissociated in a water sample. So you can have a tiny fraction of water that's dissociated into ions, but not many. So the equilibrium, if we want to think of our equilibrium arrow of how much water do we have versus how much of the products do we have, we might have an arrow that looks like this. So mostly water, tiny bit of our products. If we're thinking of this in terms of a reaction yield, we have less than 10 to the minus 5%. So really no ions at all compared to a solution of sodium chloride, which is going to have a lot of ions. Like I said, if we have 1 mole of sodium chloride in water, we're getting 2 moles. We're getting each of the ions separated. So we're getting the sodium plus cations, the chloride anions. We take 1 mole of NaCl in water. Let's say it's in 1 liter of water. That's going to be 2 moles of ions per liter of water once all the sodium chloride dissolves. So I have a lot higher concentration. I have a lot more moles per liter of sodium and chloride ions and sodium chloride than I do just in pure water. And now what this leads to behavior of the solutions, and we have a picture here. I have a little demo where we can see this kind of more in person, where we can sort of understand that the ions can actually behave kind of like a wire that can unite electrodes to light up a light bulb. And so here we have 2 light bulbs. And underneath here are the actual 2 electrodes that sit straight down. And a long time ago, they used to be exposed, these little pieces of plastic one here. So then if you were not paying attention like me and crack the electrodes, you would get zapped. And that would be good. So they hid the electrodes so that we don't get hurt as instructors if we have to grab a hold of this by accident. But if you see the 2 electrodes, all we need to do, like light bulb up, is connect the electrodes. Okay, so if we could have a wire, connect the electrodes. People use one Breaking Bad. How many of you guys have seen Breaking Bad? Oh, that's great. You guys will know the answer to the question. What would the perfect thing to unite the 2 electrodes? When Jesse's like, oh, wire. We're all trying to get him to say copper. And so, like a copper wire would be great to unite the electrodes. But water can work too. So if one of these is pure water, so this one here is pure water, and you can see here that if water were more electrolytic, it might be able to light the light bulb up, but apparently not enough electrolytic behavior in water to serve as an electrolyte to light up that light bulb. Now I can change that by adding some, sodium chloride, add some table salt, water. Working with salt and sugar, but I do have some acid solutions here that. And so the idea here is I can have my water comparison and then my sodium chloride. And so I have an electrolytic solution. I have ions that are linking that electron. Now, the actual way that the ions unite the electrons and light it up, it's kind of complicated. It's like they're exchanging electrons between the plus and the minus. And so that exchanging the electrons across the cations and anions allows that light bulb to light up. Then you might say, but water dissociates a tiny bit, but there's not enough ions. There's not enough ions to allow that light bulb to lit up. And so then what about table sugar? So what if I use table sugar instead of sugar ionized in the same way? Let's let that sit for just a minute. I'm going to rinse the electrode here to try to get residual chloride off. Let's let that dissolve for just a second. Let's play around with some other solutions. Like I have. So I have here ammonia, acetic acid, HCl, hydrochloric acid, and sodium hydroxide. And so let's compare our sodium hydroxide and our hydrochloric acid. So I have an acid and a base. And so what we see here is that I have an acid and a base solution. We'll talk about what acids and bases are as we get throughout the chapter a little bit, but they're able to light light bulbs up. So I have what I have are 2 different, an acid and base, and one was a strong acid, one was a strong base, where they're strongly dissociating into ions that allow those light bulbs to get up. The electrodes off again. Almost dissolved. Let me try acetic acid and ammonia. So acetic acid sounds like an acid. Ammonia is actually a base. We'll talk again later in the chapter about how we recognize it as being a base. Let's see if they light the light bulbs up the same way. Maybe I need to do a cross comparison. Let me do the ammonia with the sodium hydroxide. So just looking at the comparison, do you see how one's brighter than the other? And so the one that's brighter than the other is the strong base. It's the strong electrolyte. And the ammonia is actually weak. We're going to call it a weak electrolyte because it's just not ionizing as much per unit as the sodium hydroxide is. So we're going to see that we have the ability for some compounds to partially dissociate, kind of like water, where it's partially dissociating, just almost not at all. Some other compounds get a little closer, kind of in the middle of being maybe 10 to 50% ionized, and then things like sodium hydroxide, HCl, are able to fully dissociate in the solution. Let's take one last. have a compound that's soluble in water, doesn't mean that it's going to serve as any type of electrolyte. So we have, so just because the sugar dissolves in water doesn't mean it has to be electrolytic. It doesn't mean it's making ions. It just kind of goes back to that statement on our previous slide that said that molecular compounds mostly don't dissociate into solution when they dissolve. They might, and when they do, we're going to understand that that's going to be because they have an acid or a base property, or they're behaving as an acid or a base. But every other molecular compound, like table sugar, dissolves in water. Just it's the individual sugar molecule surrounded by water, but not ionizing in the process. Okay, so what do we see here? We see a strong electrolyte is a solute that fully dissociates in water. It's something like an ionic compound that's dissociating into its two ions. So an example that we saw here was sodium chloride, solid dissolving into water, liquid to form sodium plus cations, and chloride minus anions. And so another example that we saw was a weak electrolyte. Now an example of a weak electrolyte was the ammonia, and it was also the acetic acid. I didn't put acetic acid beside HCl, but it was almost as dim as the ammonia solution was. And so ammonia and acetic acid are two examples of our weak electrolytes, where acetic acid is doing this dissociation. It's forming the acetate ion and H plus ion, and it's just mostly over here and maybe somewhat on the side of ions. So we have a back and forth in equilibrium that's taking place where we have some ions form, but not as many ions as possible. We still have some of the intact acid present in the solution and then some of its ions. If we contrast that to HCl, which is like NaCl, where these are both strong electrolytes completely dissociating, HCl in solution, if we imagine the way that solution of HCl was prepared was by taking gaseous HCl. HCl actually can be bottled into a gas cylinder. If you take HCl gas, bubble it into water, a lot of it sticks, and when it does, it fully dissociates into H plus AQ and then Cl minus AQ. You never have the intact HCl molecule in the solution. So that molecule is actually dissociating the moment it contacts the solution, and that's why HCl actually has a pretty high solubility in water. And so we get the complete formation of ions for sodium chloride and NaCl, so that we don't have the intact like molecule unit or formula of HCl or NaCl in solution for those strong electrolytes. So strong electrolytes fully dissociating, weak electrolytes partial dissociation. So partial dissociation for acetic acid and also for ammonia. So ammonia reacts with water. We actually have water in the reaction for ammonia. It's forming ammonium, NH4+, and then the counter ion to water being OH-. So it's taking an H+ off of water and then forming the hydroxide ion. Okay, and so it's just doing so with a partial reaction. Anytime we have an incomplete reaction to the ions or a partial formation of ions, I just signify that with a equilibrium arrow, signifying that the reaction goes forward and then sometimes the products recombine and reform the reactants. The HCl example, imagine you make the ions, they bump into each other, they just bounce off. They don't want to be back together. They don't want to form HCl again in solution. And so we get partial dissociation. Now, at this point, let's try not to feel like you have to predict just yet what does the full dissociation with what does the partial. Try to, at this stage of the slide, or this stage of the notes, try to understand. We're just trying to understand that different molecules have some different properties here, that we're not yet really trying to get to a predictive mode yet of where we can look at a molecule and predict, is it a strong or weak electrolyte, or is it a non-electrolyte? The key I want us to do is at least try to make sure we can recognize the ionic compounds versus the molecular. That a molecular compound has non-metallic elements, an ionic compound has metal and non-metal elements. So as long as we're able to predict molecular versus ionic, we at least can get the category that the ionic compounds have to be up here if they're dissolving. They have to completely dissociate. And then the molecular compounds is a little complicated. We need to go through and understand really how acids behave, how bases behave, and then look at some examples and maybe make some list of examples of those. So then we have non-electrolytes. Those are things like the sugar, like methanol, the things that weren't dissociating at all. And so these are things like methanol, C12H22O11, that's sucrose, that's table sugar. You can have these things dissolved in water where they're not dissociated. So you get 0% or nearly 0% dissociation for these molecules, so no ions forming in solution. They're not electrolytic because they're not letting the light up. And then lastly, the term we give some compounds are just insoluble. So not everything dissolves in water. You know, like we mentioned before, like octane, like oils and water don't mix very well, or they don't even really mix at all. So some things don't mix together. Now, we're not trying to predict yet which things don't. It's just some things will turn out to not be soluble in water. Some of those things that are insoluble in water will be ionic compounds, we'll see. Like not all ionic compounds are soluble in water. Those that are, we'll see, are strong electrolytes. So like all the ionic compounds that actually are able to dissolve in water do so because the water is like plucking them off. The water is like chewing up the ionic compound, making up those individual ions surrounded by water, those water spheres. But some ionic compounds we're going to see are just insoluble in water. So for ionic compounds, we're going to see a chart, I think it's the next slide, of predicting which compounds are soluble, which compounds are insoluble. So we're going to predict these for ionic compounds. So we're going to predict ionic compound solubility. We'll see that with the solubility chart here in a second. We're not going to predict, for the most part, molecular compound solubility. Like we're not going to look at most molecular compounds and look at a formula and say, is this thing soluble or insoluble in water? It's actually a complicated question. Ionic compounds are actually fairly simple because if you look at their ions, they're usually very predictive for the type of ions that a compound contains. Those usually tell you whether or not the compound's soluble or insoluble. And so for this chart here, notice that we have a list of soluble ionic compounds on the top half, and then a group of compounds that are generally insoluble when they contain certain ions. So let's look at the soluble compound categories first. So we have nitrates and acetates. Like any metal cation paired up with nitrate or acetate is soluble in water without any exceptions. So think of any metal cation. Think of silver nitrate. Soluble in water. So if it's soluble in water, you might write an AQ. If you think of, I don't know what cations you can think of, like copper 2. Copper 2 plus, so acetate C2H3O2, copper 2, that is water soluble as well. So any metal cation paired up with nitrate or acetate leads a compound to be soluble in water. Now, one thing you have to keep in mind a little bit is that just because a compound's soluble in water doesn't mean an infinite amount of the compound's soluble. Every compound has a limit on its solubility, and even the compounds we're going to call insoluble have a very low solubility. So you can imagine that what scientists or whoever made this chart does is they look up all the different like nitrate solubilities, and they kind of go to the compound that has the lowest solubility and say, well, that's still pretty soluble. So we call all nitrates water soluble. But you can imagine that across the board for nitrates, some are slightly lower on the solubility scale, some other nitrates are higher on the solubility scale. Like if you look at chlorides, sodium chloride actually has a humongous solubility in water. It's like 600 grams of sodium chloride will eventually dissolve in like a kilogram of water, which is like a ratio of 6 parts sodium chloride to 10 parts of water. Like that's crazy. That's a really high solubility. Other compounds that we still call soluble might have a solubility as low as about 5 to 10 grams per liter. So solubility is a range. This chart here is trying to make us think it's just a yes or no. And so just realize that some of the compounds we call quote unquote insoluble still have some really low solubility, but still like an actual solubility. This is a topic we come back to in chapter 17 and 1220. Where you actually can quantify the difference of those slightly insoluble to low solubility compounds and actually kind of look at their solubilities and predict some properties and take advantage of those solubilities for separating solutions and fun problems you'll see in 1220. Things we don't need to worry so much about now, but I just want us to know that things that we'll call insoluble do have some low solubility. Chlorides, bromides, iodides are mostly soluble. but they have 3 exceptions. And the exceptions are silver plus, mercury 1. This is why we actually learned how to name mercury 1. I alluded in chapter 2 when we were learning about mercury 1, it was because of an example in chapter 4. This is that example. And then the lead 2 plus cation. So if you pair any metal up with chloride, bromide, iodide, it's water soluble so long as it's not silver, lead, or mercury 1. Okay, so if you have silver chloride, that would be insoluble in water. We would write that AgCl solid. It wouldn't be AQ, wouldn't dissolve in water. You could have lead bromide be an example of something that's insoluble in water. You could have mercury 1. Mercury 1 is weird, remember? So let me write this one up here. So the mercury 1, remember that's the Hg2, 2 plus cation. So a 2 plus would pair up with something like iodide minus. So it would be Hg2, 2 minus. So interpret Hg2, 2 plus, kind of like the way we interpret like peroxide ion, where it's just some molecular cation. 2 mercuries bonded together, some sort of bond here, plus charge on either side, iodide ion on either side. So that's why we'd write the formula Hg2I2 as opposed to HgI. And so this compound here would be insoluble in water because that cation's an exception for those ions that makes it insoluble instead of the usual rule of being soluble. Now, the one thing that's weird with mercury is mercury forms 2 common cations. The other one's mercury 2. So the mercury 2 cation's not an exception. So if you see a compound like HgCl2 and you're predicting its solubility, think of it this way. Is that Ag plus? No. Is that Pb2 plus? No. Is that Hg2 2 plus? No, it's just Hg2 plus. This compound's water soluble. So do you see how that's not one of the exceptions? So that's the weird thing. Mercury is the only one here that commonly forms 2 different charge states. Silver really is just silver plus. Lead will form 4 plus in highly acidic environments and like batteries that have some utility. But in common solutions, you're not getting any other charge on lead other than 2 plus. So you don't have to worry about different charge states for lead or for silver, just for mercury where it has these 2 common different charge states. We'll see oxidation states, another word we can use later in the chapter. So the Hg2 plus chloride is soluble in water because it's not one of the exceptions. Then anything else, copper 2, copper 1, iron 2, iron 3, manganese 5, you name it, with chlorides, bromides, iodides would be water soluble. Sulfate has the general solubility trend of mostly being soluble. Its exceptions are the mercury 1 and lead, but strontium and barium. So strontium and barium being alkaline cations turn out to be insoluble. If you look in other books, you might see silver listed sometimes. Silver sulfate is kind of like right on that edge of solubility where it's like high enough, some books call it soluble. It's low enough, other books call it insoluble. Just know silver sulfate has a relatively low solubility. Like you'll see that come up in like chapter 17 later. So you can probably imagine that even a lot of compounds we would call soluble still have a pretty low solubility. Calcium sulfate happens to be in that same category, where other books, if you look in other charts, occasionally a master in chemistry problems that get mixed in that shouldn't really, like master in chemistry works for several different books, and all these books disagree in these stupid solubility charts and solubility rules. Some books list calcium sulfate. Every now and then a problem on mastering might expect you to answer calcium sulfate as being insoluble, even though our chart says it's soluble. But when those problems come up, I usually try to delete them and make sure those aren't on our homework. So I don't think they'll be on there this semester, but occasionally in the past, old problems have made it, or from other books that have slightly different solubility charts. But just know the different solubility charts just come from a slight different interpretation of what it means to be soluble versus insoluble. So these are the 4 for sulfate. Let me make sure I say this. You get this chart on tests. We don't want you to memorize this chart. We want us to understand the utility of this chart and how we use it. We use this chart to predict that for this chart, anything other than those 4 cations paired up with sulfate would be water soluble. Those 4 cations would be insoluble. So strontium sulfate, insoluble, but calcium sulfate we should treat as being soluble, an AQ, so soluble in water. And then we have 4 ions that are given below for making compounds that are generally insoluble. Okay, and so we have, and I've never understood why the book hasn't rearranged itself. For sulfide and hydroxide have the same exceptions. I don't know why one's at the top and the other's at the bottom of the chart. Why don't we just put them together? Because if you notice, the exceptions for sulfide and hydroxide are the same. Compounds of ammonium the alkali cations and calcium, strontium, and barium make those compounds soluble instead of their general rule of being insoluble. So most compounds that contain sulfide, hydroxide, carbonate, phosphate are insoluble. The exceptions here are soluble. Okay, so KOH, soluble. But if we had copper hydroxide, that would be insoluble. So the exceptions for the cations or the anions below are soluble, and then the general rule, though, is insoluble. And so then the exceptions for carbonate and phosphate are just ammonium and the alkali cations. Yes? What's that? Yes, copper's not on the list because the exceptions are soluble. Everything else is insoluble.
But you said COH is soluble. It is insoluble.
Okay, let's do this one more time because I don't know if I'm just not being clear or if. So if we pair cations up with sulfide, carbonate, phosphate, hydroxide, those compounds are assumed to be insoluble unless they're one of the exceptions. So the exceptions are soluble for the cations below. So notice we have soluble compounds on the top and then generally insoluble compounds below. So anything paired up with these cations here is taken to be insoluble unless they happen to be one of these exceptions. See, so it's just like the tables are inverted almost. The top half mostly soluble, the bottom half mostly insoluble. And so that's why copper's not on the chart, because it's assumed to be insoluble, because it's not one of the exceptions. Now, the one thing that I've also not understood why they don't put into the chart, and then therefore this doesn't always, I don't think this is on the chart you get with the test, is that the ammonium and alkali cations with essentially any anion are water soluble. So all ionic compounds containing ammonium and the alkali cations are generally water soluble. I'm going to say with no important exceptions or no exceptions that you need to worry about. There are exceptions, but they're not worth dwelling on. Like some goofy big anions are going to be insoluble with potassium sometimes. But it's not worth, so practically anything that we have seen before, like take sulfite. Sulfite's not here. If you pair sulfite with potassium, it's water soluble. If you pair, what's something else that's not here that we've seen before? Phosphite, chlorate, perchlorate, chlorite. Take those ions, pair them with alkali cations, so lithium, sodium, potassium, rubidium, cesium. So pair those up with the alkali cations or ammonium, and that makes the compound water soluble. And then ammonium is weird, right? Ammonium is the one weird cation that's going to make a compound be ionic yet not contain a metal. So ammonium is a little peculiar in that you can have a compound like ammonium, say sulfate. So ammonium sulfate would be NH4,2SO4. We could pick a million compounds containing ammonium just with any other anion. But this with the 2-, that this compound here is an ionic compound. Like doesn't have the metal, non-metal, so ammonium is the weird one because it's a molecular cation, so this has the cation anion. So the rule for ICs is probably better the compounds that contain cations and anions. But for the most case, that's metals and nonmetals, metal cations, nonmetal anions. In the case of ammonium, molecular cation, and in the case of sulfate, a molecular anion. So ammonium sulfate, we'll call this an ionic compound, just to make sure we're clear on the ammonium still being ionic in their nature. And when ammonium sulfate hits water, it's water soluble, so we're getting ammonium separating, we're getting the sulfate that separates. So what does ammonium sulfate look like in water? Well, it looks like the ammonium cation and sulfate anion. We're just getting twice as much ammonium because of the two ammoniums compared to the sulfate. So when we see a compound like KNO3, calcium hydroxide, that those compounds are dissociating into the anions that we were learning how to, the cations and anions that we learned how to name in our nomenclature. So for example, we're asked this question here, identify the compounds as soluble or insoluble, and let's even go the step further of saying, well, what does the thing do in water? Like, what does it look like in water? So KNO3, two ways we know that's soluble. Contains potassium, should be always water soluble. Contains nitrate, always water soluble, with no exceptions for either. And so this compound here is soluble. And so then in water, KNO3 is going to exist as potassium plus and nitrate minus. Like, that's how the IC dissolves. You have those strong plus-minus interactions. Ionic compounds have high melting points and boiling points because those strong ionic forces of attraction, they can only break those forces if they're being surrounded by water molecules. So the only way an ionic compound would ever break its attraction with its neighboring cations and anions is to form a mutually attractive force between water. And so we're getting these aqueous cations and anions. Calcium carbonate, now again, I don't really expect that we memorize the chart, but carbonate, phosphate were the two that only had the exceptions of ammonium and alkali cations. This is an alkaline, close to an alkali, but an alkaline, so this would be insoluble. So it goes back to the chart. By the way I'm recording, it makes it painful for the video if I go back, but so I won't go back. But you can look back in your notes that calcium 2+ is not a listed exception for carbonate ion. So that would be insoluble because carbonates are generally insoluble. Cesium hydroxide, now we just have to remember cesium is in that alkali group with sodium and lithium and all that. So it's not the most common example, but this would be soluble. And anything containing cesium should be taken to be water soluble. And so this exists in water as cesium plus and OH minus. And so in the solution of calcium carbonate, there's no solution. If you have calcium carbonate water, you would have calcium carbonate at the bottom, presumably, and then just water on top. So you'd have like a heterogeneous solution. It wouldn't even really be a solution. It would just be solid in solution. And now when I said calcium carbonate generally at the bottom, most metals have a higher density than water, so they'd sink. Occasionally some metals are weird and have a lower density and they float. So that happens every now and then. So a solid can float, it's just as a matter of its relative density compared to water. What about silver sulfate? You just have to remember some, like the chlorides, bromides, iodides are insoluble paired up with silver, but not sulfate. So this compound here, we would take this to be soluble. Like I said, you'll see in chapter 17, it's not very soluble. It's kind of right on the edge of compounds that you would argue about as being soluble versus insoluble. So this would be taken to be in solution, 2 silver plus cations and a sulfate anion. And it would never be, like, we sometimes write this. Like, we can write a molecular formula like AQ, and sometimes like we'll write reactions with these. We'll call it like a molecular reaction. It's almost like molecular in quotes, because it's really not molecular. The cations and anions really aren't paired together in this solution of this ionic compound. They're really this. So we might write, and we do this a lot of times, we'll write KClAQ. But we have to think that that's like colloquial. That's just like a way of representing the solution that we really know is an ionic compound in solution. It's dissolved, so it's really K plus and Cl minus. So we can write solutions this way. We can write, KCl, AQ, and then just understand it's really K plus Cl minus AQ 100% of the time. So we might write this, but it's really this in solution. This is such an easy question. I don't think I need to take a break. Maybe we'll take, let's see what time it is, like 30 seconds for you to think about this question of what exists in a solution of KNO3. All right, so is this answer pretty obviously C? Like, it's not a trick question. Now, sometimes, especially once you get removed from the lecture and you come back to this like a day or two later, you're doing some problems like a week from now, sometimes you'll say, well, how do I know nitrate doesn't break apart into like N3 minus and O2 minus? Like, we've seen those ions before. How do I know that this doesn't turn into that? Well, one way you can know is that it doesn't make any sense. Like, how do we go from a minus and we're making other minus charges? Like, where's the plus charge go? Like, it's just the charge balance doesn't even make sense. And then, you know, when we learn how to name ions, it's because they're stable. Like, if something's stable enough to form a solid with a cation, it's probably stable enough to exist as that ion in water. And so these ions have some stability. That's why they exist. That's why cations can pair up with them. And so that's why we're staying with nitrate. Now, you may also look and say, well, doesn't water dissociate a tiny bit? Aren't there some of these ions in solution? There are some, but I think the best answer to the question is the one that there's really a lot of, not the ones that there are a tiny, tiny little bit of. Okay, and so K plus and NO3 minus I think would be the best answer for this question. Okay, so let's get into the topic of predicting precipitation reactions, because we can use the solubility rules to look at two solutions that are mixing to try to predict if an insoluble precipitate should form during the course of the reaction. And you guys saw this in the lab already, where you took Ki and lead nitrate and you mixed them in water, and then you got the pretty immediate formation of that yellow solid of PbI2. And PbI2 was forming, as you can see now, because it's insoluble in water. And so we start with Ki, that's AQ, right? Like, potassium's not an exception of iodide, so that's water soluble. Lead nitrate, all nitrates are water soluble, so we start with two salt solutions mixed in water, and then when the lead ion in the one solution finds the iodide ions, they crash out of solution and form that precipitate and start to collect at the bottom of the flask. So here we're forming the insoluble PbI2 because that's insoluble in water. And so a precipitation reaction has to form a precipitate. If one of the products on the product side of the reaction, if you're imagining switching your anions between two metals in this metathesis or exchange reaction, so if we're imagining exchanging the nitrate ion over to the potassium and then the iodide over to the lead, if neither one of those compounds on our product side were insoluble, then the reaction would just be a mixing of ions. We have to have something change. You know, so if both of our products are AQ, both of our reactants are AQ, then nothing's really reacting, nothing's changing. We're just literally taking a solution of ions, another solution of ions, and mixing them together. And then no products are really forming, there's no change. So I have to have a solid form. So a solid forming is required for this reaction. That's why it's called a precipitation reaction. Now, sometimes the same word for this reaction is used of a metathesis reaction. I think metathesis implies a change, you know, so there has to be a change taking place during the reaction, otherwise there's no actual change, no change was taking place. And so how do we predict if a precipitate forms when strong electrolytes, when these solutions are mixed? Well, we note the ions in the reactants. We consider the cation anion rearrangements. We just are switching the plus and minuses around. And then we use our solubility chart to predict our solubilities. And so we're said to consider magnesium nitrate reacting with sodium hydroxide. And so we have sodium hydroxide in our reaction here. Now, is this solid or AQ? It's AQ, it's water soluble. In fact, you can almost imply that because we're mixing them in like solutions of them in water. Magnesium nitrate, all nitrates are water soluble. So usually we have two AQs, but we could dissolve a precipitate with a solution or something. So we can imagine taking a solid plus an AQ and going to two AQs. That would be the opposite of a metathesis reaction. It would be a dissolution of a solid. But generally speaking, metathesis is going to have two aqueous solutions here on the reactant side. And then something has to precipitate. And if something doesn't precipitate, no reaction is taking place. And so for hydroxide, if you recall, the exceptions for hydroxide in the solubility chart are ammonium, alkali cations, but calcium, strontium, barium, not magnesium. So it doesn't list magnesium. So we're interpreting magnesium to be water soluble. So magnesium, not an exception. For the hydroxide ion on the solubility chart. So therefore, it has to be assumed to be the general rule for hydroxides of being insoluble. Sometimes we write test questions just like, which compounds are water soluble? Or like, is this compound water soluble? And magnesium hydroxide, a lot of people think it is. Just go back to the solubility chart, and for our solubility chart, is it soluble? No. And then sodium nitrate, of course, would be water soluble. You could have two solids form. That would be kind of peculiar because they would form and intermix together, and you'd get kind of almost like an interesting crystal that would be the amalgam of the two crystals. So you really wouldn't kind of get either of the two products. You get them mixed together. But usually you're going to have one solid. You could have both of them be solid. But in the most common form of precipitation reaction, you have just one of the products is a solid. But that's the requirement. If they're both AQ, no reaction takes place. And so for this reaction here, we would say yes, a metathesis reaction, magnesium hydroxide would precipitate from the reaction. Okay, so if we took a solution with strontium nitrate, so we have strontium nitrate in solution. If I mix it with which one of these compounds is going to lead to a precipitate? So you can refer to the solubility chart here. Take like a minute or two on this one to try to think if you can spot which of these, which one of these solutes should lead to a precipitation reaction. All right, let's take a, I think a few of you might still be working and trying to identify it. Let's look at KOH first and try to see why KOH actually doesn't work. So if I'm imagining KOH, both of these two solutions reacting together, do I get a solid that forms? Well, it's never going to be with the nitrate, right? Like the nitrate is always water soluble. So if we pair up the potassium with the nitrate, of course that's going to be AQ. Anything I pair up with the nitrate is going to be water soluble. So I have to like pair something up with the strontium. So I have to make something insoluble with the strontium. So if I make strontium hydroxide here as my product, that's water soluble. That's not insoluble. So that's not insoluble. This would be AQ. And just AQ to AQ, nothing solid, there's no reaction taking place. We're just mixing solutions together. We're not really forming this and this. We just literally have we have a solution of strontium, nitrate, potassium hydroxide ion where they're just all floating around each other. Okay, and so no reaction really has taken place with the KOH. And so then if I think about acetates, so I have lead acetate, calcium acetate. Lead acetate seem probably really, like, a lot of people might circle lead nitrate, but this is wrong just because of the lead, because you know lead has some exceptions. Lead has exceptions in a bunch of categories. But lead nitrate is water soluble, and strontium acetate is water soluble. So if I imagine writing in lead acetate here, then both of my products are still going to be AQs. So I'm going to have lead. So I'll have lead nitrate down here. That's water soluble, of course. All nitrates are water soluble. Then I'm going to have strontium acetate. That's water soluble. All acetates are water soluble. So the acetates don't work either, because all nitrates are soluble, all acetates are soluble. So I can't get a precipitate to form of nitrates and acetates mixing together, but then the K2SO4 is the perfect pair. So K2SO4 is the answer to the question here. So if I take K2SO4, I still get my KNO3AQ, but strontium sulfate is one of the listed exceptions for sulfate ion as being insoluble. So strontium sulfate is properly insoluble to allow a precipitate to form. And so I don't get precipitates with A, B, or C mixing here with strontium nitrate, but I do with the potassium sulfate. So we have to consider just this switching of the sulfate and then the nitrate ions, and do those products form something that's insoluble. Okay, so now let's look at these reactions on more of a molecular level at what's going on in their solutions. And so let's consider the reaction lead nitrate and Ki, the one you did in lab, and try to write things like full molecular reactions and think about what's going on at the ionic or the molecular level. And so the way we wrote this reaction before was we took lead nitrate, AQ, Ki, AQ, we form PbI2, solid, that's our precipitate. So we need 2 Ki's, and then we form KNO3. And so this way of writing the reaction here is what we call the full molecular reaction, but it's not molecular. These are ionic species. They don't really exist as molecules. And so this is kind of where I put that almost in quotes, so that where I look at this reaction as the full molecular reaction, because it's not really occurring at this molecular level. Like a solution of lead nitrate isn't PbNO3 It has the ratio of 2 nitrates to 1 lead, but it's really lead ions and nitrate ions. So when we get towards the net ionic reaction, it's really imagining that my lead nitrate really dissociates into its ions. Remember, any ionic compound that's AQ, that's soluble in water, dissociates into its ions. If it's insoluble, then it doesn't dissociate because it's not in the solution. But if it's AQ, soluble in water, dissociates into its ions. And so then my Ki is really 2K plus 2I minus ions. So I'm just taking into account 2 in front of potassium and iodide. And then my PbI2 is just PbI2, because it doesn't dissociate because it's a solid. It's at the bottom of the test tube, so it's not in the solution. And then KNO3, I forgot the 2 in front of it, but 2 KNO3 would be 2K plus 2 nitrate. And so if we look at the full ionic reaction still doesn't dissociate the insoluble compound. So the full ionic equation looks like this, where we just ionized our strong electrolyte water-soluble compounds. And then I could go to the net ionic by canceling out the spectator ions. The spectator ions is simply are the ions that do not change during the reaction. So potassium and nitrate don't just disappear spontaneously, they just are canceled out from the net change of the reaction to the net ionic reaction. So the net ionic reaction would be Pb2 plus 2I minus. Now I could write AQs. A lot of times with charged species, I'll leave off the AQ tags just for brevity, just because if it's charged, it has to be surrounded by water. And then we're forming PbI2 solid. So notice I didn't bother writing all the AQ tags here, but all those charged ions are AQs, of course. And so our spectator ions, like I said, they don't just spontaneously disappear, they just are canceled out as being not part of the net change. So the net change of the reaction, the net ionic reaction, is just what actually is changing at that sort of ionic level. So K plus nitrate, same forms both sides of the reaction, they're canceled out in this net ionic reaction. Okay, so we'll write next as we proceed. So we'll look at some more net ionics and identify spectator ions, and we'll get into acid-base reactions on Monday. All right, guys, that's the start to chapter 4. Have a great weekend.